Good morning, everyone. I hope you are enjoying the third and final day of ASPLOS. I hope you all found something to eat this morning, so you're in a good, happy, well-fed mood. It gives me great pleasure to announce our speaker for this morning. It is Bryan Catanzaro. He's Vice President of Applied Research at NVIDIA, where he leads a team of researchers working on chip design, audio and speech, language modeling, graphics, and vision, with the goal of finding practical new ways to use AI for NVIDIA's products and workflows. Before working at NVIDIA, he worked at Baidu, working on creating next generation systems for training and deploying end-to-end deep learning based speech recognition. And before that, he was at NVIDIA again, working on programming models for parallel processors. He got a PhD from Berkeley, working on the Copperhead language and its compiler that allows Python programmers to use nested data abstractions. So without further ado, I will let Bryan tell you about his work for a while.
Thank you, and good morning, everyone. I'm excited to be here. ASPLOS is maybe the perfect place to talk about all of the things that are necessary in order to change the world with language modeling, because these models are so computationally interesting and so computationally difficult, and optimizing them requires a really broad range of technologies to work together. So that's what we're going to be talking about today. So I'm assuming that all of you guys have played around with ChatGPT, and you know, when I think when it was released at the end of last year, it was kind of a shocking moment in the history of artificial intelligence, because all of a sudden people could touch and feel and interact with the power of these language models in a way that felt useful and interesting to them. Now, the field has been dreaming about language models that could actually solve problems and answer questions and could translate between languages and, you know, could reason, could write poetry. The field has been dreaming about that for a long time, and ChatGPT is, you know, not coming out of nowhere, right? It's building on years and years of research, but it was the first moment when ordinary people could touch this technology and recognize there's something special here. And because of that, it became the fastest growing application in history, you know, much faster than TikTok, much faster than Instagram or Snapchat, Facebook, WhatsApp, all of these things that have created extraordinary value. But the growth of this language model really took many people by surprise, including, I think, also the people at OpenAI. I've had a few of my friends there tell me they weren't expecting people were going to care about this demo so much, because to them it was just another demo in a long line of demos that they've been thinking about and working towards for years. But there's something about, you know, this technology that's finally reached a point where people can touch it and understand it and interact with it, and they can think about, what does this mean for my work? In response to that, over the past few months, we've seen a lot of announcements from a lot of big companies and a whole raft of startups that are thinking about how to change their work using language models. Obviously, Microsoft and OpenAI have teamed up. Microsoft's putting GPT-4 in Bing. People are starting to interact with it. Sometimes it's amazing, sometimes it's broken. That's the way technology works. But when it works, which is a lot of the time, it's really quite extraordinary. Facebook or Meta announced that they're making a top-level product group focused on generative AI. Google also has been showing demos of their own AI, which you know, they have some pretty great models as well. And you know, the future of search, of advertising, of social media, all these things that are important to the tech industry today are all going to be different because of these models. And actually, when we think about what are these models for? They really are new ways of building tools for intellectual work. And you know, there's so many of us these days that do intellectual work on the day-to-day business. I would claim all of us in this room are part of that. You know, if you write emails for a living, or if you write papers for a living, if you write computer code for a living, you know, this is intellectual work. And we know that we need better tools. We know that we need more productivity. I think every group that I've ever worked in every academic or industry setting, has felt constrained by lack of resources. We felt like we didn't have enough people to do the interesting work that we'd like to do. I think, certainly at most companies, most groups will tell you, if I had twice as many people, I could do so much more interesting things. And yet we have, we have problems finding enough people. We have problems, resources to actually do all the work that we could dream of. So we need to find ways of being more productive. And any tool that we would invent that could increase our productivity, we're going to call that tool AI if it's increasing our intellectual productivity. And language is underlying all of our intellectual work. So all the things that we do when we're thinking, we can describe in language, we can ask questions, we can answer them in language. And because of that, these language models are going to change the way that we do all of this work. And it's very exciting. It's also scary. There's a lot of people that are worried about that. And I sympathize with that. I think, any technology that's going to be deployed this broadly and this profoundly is also going to come with change, and it's going to come with risk. And it's going to take some time to figure out what that means for all of us. And so I hope that we can navigate that compassionately and carefully. And I don't want to minimize that, but then at the same time, the history of humanity is that we find technologies that help us be more productive and help us do new things, and that leads to extraordinary growth and change. My job working in artificial intelligence is something that my grandfather never would have conceived of, and yet I really like doing it. And the only reason that it's possible is that there were technologies that automated a lot of the things that he was doing, so that the world could dream up new things to do, like artificial intelligence. So I am not worried about we're running out of work. I think there's far too much to do here, but we need better tools, and that's what these models are doing. But today, I'm not here to just plug language modeling and how extraordinary the applications are for language modeling. I think that's been done pretty well, and hopefully you guys have already experienced that. What I'm going to be talking about today is about the systems, the compilers, the libraries, the chips, the interconnects, the algorithms that underlie this, and kind of hopefully motivate you to feel that this is an exciting place for you to apply your skills. ASPLOS is kind of an interdisciplinary conference. There's a lot of different kinds of computing systems technologies that come together to make things like this possible. And I think there's a lot more work to do here. So I think there's a lot of opportunity for you guys to help move this forward. Now, when we think about ChatGPT going from 0 to hundreds of millions of users in such a short period of time, that is going to reflect a lot of compute demand. It's going to reflect a lot of compute demand just for running inference. These models are not small, and it takes a lot of work just to run the model and answer a question. But we're just at the beginning. At the moment, hundreds of millions of users are playing around with the demo. But when this is integrated into the work of billions of people around the planet, the aggregate inference demand is going to be quite extraordinary. And we're just at the beginning. In the past, and much of my talk is actually going to focus on things that we've done in order to improve training efficiency, because training these models is so extraordinarily expensive. So in the past, a lot of the work has been focused on training and how we can train these models and make them bigger and better. I think that going forward, inference is going to be even more interesting computationally, and there's going to be a lot of systems problems in there as well. So I'm going to try to talk about that today. We are also just at the beginning of the way that these models are coming together. So ChatGPT, when it first came out, was text only. And then, maybe you've seen there's been GPT-4, which has this multimodal component. So it can actually, it's kind of like giving the language model eyes. So it can see things, it can read graphs, it can read text, it can read pictures and kind of understand things that are inside the pictures. And then you can ask questions about it, ask it to solve problems about what it sees. So clearly, if you have a model that can answer questions and solve problems. Giving it eyes is a good idea so that it can understand a broader range of questions. But there's other things we'd like to do as well. Making it even more multimodal, having it understand video so it can learn better models of physics and sort of be more grounded in the real world. Things having to do with audio. There's other interesting modalities as well. And so the workloads are changing, and I expect they're going to continue to change for a while, which is also interesting from a compute point of view. Okay, so how do we go about doing this at NVIDIA? NVIDIA is an accelerated computing company, and our goal is to do the computationally impossible. So there's a thing, it's an important thing. The world wants this thing, but there's just not a way to practically do it. We just don't have the computing power to do that. How do we go about solving that? And the way that we do that at NVIDIA is by full stack optimization of all of the components in the system. Of course, that involves chips. We're very proud of our chips. We make awesome chips. It also involves systems. How do we package the systems together? It involves networking. How do we connect systems together in a data center? It involves data center design, cooling, and power, those things. It also involves tons of software. Software for libraries for communication and computation. Our programming environments that allow people to write parallel programs that run on these systems in a productive way. Things like PyTorch, the frameworks that these AI systems are built out of that are higher level environments, usually written in Python, that allow people to think about their problems in a form that's closer to the machine learning itself. And then we have the algorithms that are going into these systems. What kinds of models are we building? How are they being built? Are we using mixtures of experts? Are we using sparsity? What kinds of numerical precision are we using? And then the applications itself, what is the context in which these models are being put? What are their inputs and outputs? How are they being sanitized? What are the guardrails? All of these things are connected. And the way that we deliver transformational speedups is by considering them together, which is why I'm happy to be here at ASPLOS, because I feel like that's what you guys also do, right? You guys there's experts in practically every part of the space here today. And so the conceit of accelerated computing is that the only way that we can actually solve these problems is by co-optimizing everything. And that's what we aim to do. I think it's important to note that this is mostly software. Like if you were to weigh the aggregate amount of work that I was just talking about and ask how much of this is, let's say, for example, chip design, and how much of this is, for example, writing C++ or Python code, it would be like 70% Python code and C++ and maybe 30% chip design. And I think that's often underappreciated. People focus on the chip because the chip is tangible. It's a thing that gets released. It's like a concrete thing. It doesn't happen very often. And so people think a lot about the chips, but the chips by themselves don't do anything. A chip is just, a piece of silicon, right? It needs to be running something, and it needs to deliver a transformational speed up. And in order to do that, we optimize everything together. So I wanted to go back through history just a tiny bit. In 2012, Alex Krzyzewski and Ilya Sutskever and Jeff Hinton published the famous ImageNet paper that's credited with kicking off the deep learning revolution. And back then, the model had 61 million parameters, and it took 260 petaflops to train. And it was trained on a few GTX 580 GPUs. So this was GF 110. It was a long time ago. Today, 10 years later, when we think about the GPT models, GPT-3 was 175 billion parameters, and it was approximately 300 zettaflops. So that's 1 million times more compute. So in the span of 10 years, we have increased the amount of compute going into training a model by a factor of 1 million. which is an extraordinary rate of change. And it didn't take a few GPUs to train it. It took, 10,000 Volta GPUs. And GPT-4 is even bigger. So, when we think about the rate of change that the industry has been going through and how that's translated into progress in AI, it's really quite extraordinary. And this is what we live for as we're working on accelerated computing. So let's zoom in a little bit on how the computers for this are built. Our latest and greatest GPU is the Hopper GPU, named after Grace Hopper. And it has a lot of tensor core throughput for training neural nets. In fact, if we look at its highest speed mode, it would be our sparse 8-bit floating point format, which I'll talk about in a little bit, where this chip can sustain 4 petaflops on a single chip. Along with that, we have a bunch of memory attached to it, up to 94 gigabytes of memory. And yes, 94, not 96, I know. That has to do with manufacturability. And 3.4 terabytes per second of HBM bandwidth. So there's a lot of bandwidth, a lot of compute in this chip. The chips are then put into a system. So we have invested a lot in interconnect between these chips. We have this fully connected NVLink fabric. It's got 900 gigabytes per second per GPU going into this fabric, and all the GPUs can talk to all the other GPUs at full rate. And it's also coherent, so you can share data between all the different memories attached to each GPU. So we put that into a system, and sometimes we like to think about that as one giant GPU. So all of these 8 GPUs, because of this interconnect, can access each other's memory natively. So from a programming model point of view, it's just dereferencing a pointer or running an atomic memory transaction. And you don't have to change the way that you write your program at all, which then allows us to really simplify the way that we build collective algorithms inside this box. All of this gets packaged into a box with some CPUs and some CPU memory and some flash memory and a bunch of network adapters. We call that a DGX. This thing is 11 kilowatts, so it's pretty heavy, but it's also really fast, 32 petaflops in sparse FP8 mode. But that's not enough. We then wire these things together. So the interconnect is very, very important. This is a few years ago, actually, NVIDIA acquired Mellanox, which made a lot of InfiniBand and Ethernet networks. And the reason why we did that, a lot of people at the time asked me, like, why does NVIDIA, you're a GPU company, why do you care about networking? And the answer is because it's all needing to be optimized together. When we're thinking about what does it mean to accelerate computing, if we believe that the future of computing has to do with data center scale training and inference, then the interconnect is absolutely essential to that. And so these boxes are then connected with our best networking. In this case, our Quantum 2 InfiniBand at 400 gigabits per port. And there's approximately 8 full speed ports on the back. And I think there's a couple more for management. And then we stick those together into systems that have hundreds and thousands of these nodes. So we're talking about getting tens of thousands of GPUs together in one system. Stick that in a rack with some storage. We call that our DGX supercomputer. And then we stick a bunch of those in a data center, and we call that our modern AI factory. So if you think about artificial intelligence, anything artificial needs to be manufactured, right? That's kind of what the word means. And where are you going to manufacture intelligence? You're going to manufacture intelligence in a factory that looks like this. And actually, this is what it looks like inside of the Azure data center. So this is actually an H100 setup that Azure is now providing preview access to. So you can see what it actually looks like in the real world, not just in my rendering. Okay, so that's just giving you kind of a sense of the scale of the computing systems, the hardware that are going into training and deploying these models. And it's really important and interesting, but I'm actually not going to talk about hardware for the rest of my talk. I'm just going to talk about software. Actually, I'm going to spend a lot of time talking about the algorithmic work that we've needed to do in order to make these systems scale for training and the systems that have gone into that. When we think about training language models, it can take $10 million or more of time on a computer to train a single model. So I'm not talking about how much does the computer cost. I'm talking about, like, if you amortize the lifetime of the computer and you're going to spend some fraction of its life training this one model, how much does that cost? And so if, ordinarily, if you were to spend $10 million buying a thing, and you work at a company and you go to the CFO and you're like, hey, I want to spend $10 million buying a thing. That thing is going to be pretty big. It's going to be like an office building, or it's going to be like a whole parking lot full of cars or something, right? But what do you have at the end of one of these model runs? You have like a hard drive that's full of random looking numbers. Sometimes it's a little crazy to think about it that way, but you can imagine that it's going to be scrutinized pretty heavily. Like the time that you spend training this model is going to directly impact the investment that you're making, and of course, when it gets to be this big, every percent really counts. And these models, I believe, are going to continue growing. So we're right now, it's common to spend tens of millions of dollars of compute time training a model, but we could get to much larger, much more expensive models. And I think we will, because these models are being deployed in ways that really impact everything that we do. So in order to do this, we're going to need to really focus on three things. First of all, efficiency. That has to do with the ROI. So how do we get the absolute best return on our investment in compute time? And when I'm thinking about efficiency for training these models, I think about it in a speed of light sense, which is, what's the actual maximum floating point math throughput of this aggregate system I'm training the model on? And that's going to be, 100%. And then, how close can I get to 100%? And, when you think about that, that's abstracting away thousands of layers of systems, right? Software systems, hardware systems, memory hierarchies. There's a lot of things that have to go right in order for us to approach that number, but that's the speed of light. So that's what we're going to measure ourselves against. We care a lot about scalability. So, it's one thing to run on a small system and get really good efficiency, but in order to get the absolute best models, we're going to need to make them huge. And so we're going to need to be very efficient at large scale. And then we also care about simplicity, because the algorithms and sort of the ways that we go about training these models are changing. There's a lot of different innovations in the ways that we think about what the model is, how it's constructed. The overall structure is fairly static, but there's a lot of things that we've done to make it more efficient, and we've needed systems that are very simple in order to do that. And my group, we built the system called Megatron, which we've been working on, for the past 5 years or so. And Megatron is kind of the way that NVIDIA has shown the world how we think you can get efficiency training these models at scale. And when we started Megatron, the soul of Megatron was to have no compiler in it. And you might wonder about that, especially given that the introduction said that I worked on compiler back when I was a grad student, and I did. I worked on a domain-specific compiler that did a lot of machine learning back when I was in grad school. So why did I feel like we needed to make the system without a compiler in it? And the reason was I just really wanted it to be simple. I've noticed that systems, so we can have a very high-minded system that could perform every possible conceivable transformation to this program. And one day, I think we probably will. So for all of those of you that are working on such compilers, I applaud you and I encourage you to continue doing that. However, we had a really concrete problem. We just needed to get this thing up and running, and it needed to run as fast as possible. And we felt like we could do that better just doing it by hand than building a compiler to do that. And so that's currently how the system is built. And that has actually given us more agility because we're able to change the system. We just go in and change it. And I think that's been important. It is not the case that people have not built systems for doing these kinds of things automatically. It's just that those systems have been difficult to use. They've been too rigid. So so the simplicity is really important as well. Okay, so I'm going to go into a little bit more detail about how we get efficiency and scalability. We're getting scalability using a combination of data parallelism and model parallelism. And I'll explain that in a second in case you haven't heard those words before. Inside of model parallelism, we have 3 different kinds of model parallelism. There's tensor parallelism, sequence parallelism, pipeline parallelism. You know, when we combine all these things together, you know, we've come up with a system that's quite scalable and quite efficient. So here we're showing a weak scaling plot going from a 1.7 billion parameter GPT model to a 1 trillion parameter GPT model, going from 32 GPUs to 3,000 GPUs. So it's 2 orders of magnitude in hardware, 3 orders of magnitude in model size. And we're getting almost linear scaling. And also at pretty great efficiency, and I'll talk about that in a second. Actually, I feel like I already talked about this simplicity just a second ago, so I'm going to skip this slide. But again, just to reiterate, the fact that we haven't been using a compiler for this and have been doing this by hand, I feel like points to the need for more research into scalable, flexible compilers that can do these transformations in a way that you know, we can really use, because there's a lot of them, and I'm going to be showing you what they look like. Okay, so in the machine learning world, when we talk about data parallelism and model parallelism, just in terms of terminology, this is what it means. When we're training the model, we have a lot of different examples of data. In the case of language modeling, our objective is usually quite straightforward. We're just trying to predict the next word. So we download the entire internet. We have trillions of tokens. Words are made out of maybe 2 or 3 tokens each. So we have a vocabulary of tokens, maybe like 100,000 tokens. We have trillions of these tokens that represent, you know, all of the documents that we've gathered from the internet and cleaned and deduplicated and so forth. So you can imagine that there's parallelism because we just have so much data. And so the idea is that you have multiple copies of the model, and when you're training it, you update each of those copies of the model sort of independently, and then combine the results from what you've learned from all these different examples of data in order to kind of update the global version of the model. So that's what data parallelism means. Model parallelism has to do with actually slicing the model itself up in pieces. So, you know, the model may have hundreds of billions of parameters or trillions of parameters. That kind of suggests that we could slice it up in pieces. And there's different ways we could do that. We call tensor parallelism the kind of slicing across the actual weights of a single layer of the model. So the models are constructed out of layers. They might have 100 layers or so. If I look at one layer individually, it still has a lot of compute and a lot of parameters in it. So I could cut that into pieces, and we call that tensor parallelism. We could also imagine taking the model, all 100 layers in a stack, and dividing that stack into pieces and running those in parallel, and we call that pipeline parallelism. So there's a bunch of different kinds of parallelism here. I'm going to start with tensor parallelism. When we first look, this is on the right, there's a transformer stack, and each layer of the transformer is built in the same way. And I'm just zooming in on one part of it. This is the we call it the MLP, multi-layer perceptron here. It has 2 big matrix multiplies. There's a nonlinearity in between them. And so when we're thinking about like, if we were going to split up the computation, there's different ways of doing it. We could, so we have like a big matrix multiply, a pointwise nonlinearity, another big matrix multiply, and then we have dropout here. So the XA and YB in this equation, that's where all the math is happening. Now, if we wanted to split X column-wise and A row-wise, then before we finish the computation of Y, which involves this nonlinearity, we have to actually sum those two halves of the computation together, right? So the nonlinearity, that's the point of a nonlinearity, is that you can't move the sum outside the nonlinearity, because that would break the algorithm. So we would need to synchronize before we did that. But you can imagine if we split A column-wise and then do the math independently, we can actually perform the nonlinearity on the two halves independently, and they don't need to communicate. So we don't need a synchronization point there. And it actually turns out that because we have two of these big matrix multiplies stacked next together, if we slice it in just the right way and do one of them row-wise and one of them column-wise, then we can actually see that some of the computation, some of the communication, some of the synchronization that would be necessary to form the intermediate steps can be removed. And so that takes away half of the communication that's required in order to do that. And then it sort of leads to this state where we have these F and G operators that we've inserted in here in order to keep the algorithm correct. These are our communication operators, and they turn out to be pretty simple. So in the forward pass, when we're training these models, we're doing both forward pass and backward pass. The forward pass is when we're pushing data through. The backward pass is when we have learned from the data and we're going to try to update the weights. In the forward pass, F is just the identity operator, so we're just taking that X matrix and just copying it among two processors. And then once we get to G, which is at the end of this little group here, we need to do an all reduce. So basically Z1 and Z2 need to be summed together in order to get the output. And that's what G is going to do. It turns out that in the backward pass, the identity is actually a replication operator here, so we should think about it as a replication. The replication becomes an all reduce in the backward pass, and the all reduce in the forward pass becomes a replication in the backward pass. So these are kind of conjugate. So that's the way that we deal with tensor parallelism, is that we found this trick. If you slice it in just the right way, you have half the communication, half the synchronization. Okay, that's great. But we want more parallelism. So now let's talk about pipeline parallelism. And the idea is that we're going to take our training data, and it's divided into batches. We're using some of those batches on data parallelism, so we can have multiple copies of the model being trained in parallel. But we're actually going to take the batch for each copy and divide it further into micro batches and then pipeline it. Okay, but pipelining is then going to introduce some waste. Maybe you guys remember processor pipelines back in the day when you were studying computer architecture, but anytime you pipeline something, you have this problem that you got to flush the pipeline if you need to synchronize. And in our case, we do, because we need to stick data in. That's the blue stuff, the forward pass, and then that pushes all the way through the model. And then we need to learn the objective. So we're going to learn what we did wrong, and then we're going to get gradients. We're going to push that computation backwards through the pipeline. It's going the other way. That's the green boxes on this diagram. And you can see all the gray boxes. These are just wasted compute cycles, because the gray boxes are necessary in order to keep the semantics of the algorithm, to make sure that we're actually doing the right thing. Now, some people sometimes have wanted to relax this, because they're like, well, the model's just learning, so maybe it can learn even if you don't care about the exact ordering of the updates that you're getting to the model. Just let it happen. Just let the system go and see what happens. And it turns out that those style of approaches, they introduce a lot of non-determinism into the training process, because now the answer that you're going to get is going to be dependent a lot more on the specifics of the system that you use to train it, which makes it a lot harder to debug. And it also makes the model get worse results because the copies of the weights that it's learning from are going to be different than the weights that the gradients are being computed against. So there's kind of a mismatch, and the mismatch is going to be different at different parts of the model because we have this pipeline structure. So it turns out that in our experience, it's better to not do that, and we could just go with the synchronous algorithm. Obviously that, this is the reason I'm bringing this up. This has an interesting interplay between the systems and the algorithms, right? And as I said, accelerated computing, you have to consider all of it. And this is a good example of that. So in our experience, we found, and I think in the vast majority of the work that's done today, we found that we actually do need the synchronous semantics. And so we respect them, but then that means we have these pipeline bubbles. So then we invented this interleaved pipeline schedule, which then what it does is it takes the batches of data and subdivides them even further. So we have the batch, we have the mini batch, we have the micro batch, now we have like the nano batch. And then sort of round robins each of these nano batches amongst the different processors that's in our pipeline parallel group. And as you can see, this schedule then compresses the training time. There's less of that gray area of wasted space. Okay, so when we're thinking about like what does this mean for the system that we're using to train this model, it is doing some complicated things, right? So we've expressed our transformer, we've sliced it up with tensor parallelism. Now we've sliced it up again using pipeline parallelism. Now we've introduced, a non-trivial scheduling onto here that is giving us quite a bit more efficiency. This is the kind of thing that I'm talking about. Now, could you do this automatically with a system? Yes, you could. You could absolutely do this with a system. In fact, maybe you could build a system just for doing those two transformations. And maybe we should. At the moment, we're doing this by hand. Okay, so interleaving gives us better results, especially at small batch sizes, which is good for strong scaling. And I'll talk about that in a second. Okay, sequence parallelism. So it turns out that activation memory is a big problem for these models. In order to do the backward pass, we have to save the activations of the forward pass so that we can compute the gradients as we come back. And saving those activations takes up a lot of memory. In fact, if you look at this chart, there's this little red line here. That's showing the space that we have on our A100 or H100 GPU. And the green line is bigger than that, which means we just can't fit all of the activations in memory. So what it was standard practice was that we would recompute them. So it's like basically a tax on our compute budget because we don't have enough memory to store these activations, and we can't stash them in some other memory because it's not fast enough. So we need something really fast and really big. And so this was causing a 30 to 40% computational overhead because we had to do this recomputation. And the solution to that was to use sequence parallelism. And I'll explain what this is in a second, but the result is that we're sustaining 56% of our peak arithmetic throughput for the entire cluster, which I think is pretty amazing given how arithmetically dense these processors are. And the reason we could do that is because we're not doing much recompute at all. So how does that happen? Well, before what we were doing, I was talking about tensor parallelism, and that really only applies to the sort of shaded regions in this plot. And all of the other things that are not shaded, their activations had to be duplicated in order for the algorithm to be correct. But what we noticed is that all of those things that are not shaded actually don't have dependencies in the time dimension. In the sequence dimension, we're training these models on sequences of data. It turns out that those operations are independent in the sequence dimension. And so we could decompose the problem along the time dimension and in those particular areas. And that could reduce our duplication. Because right now, if the rest of the model is duplicated, but we across all the processors, but we have to basically hold the activations for each of them, then that's quite expensive. And so it turns out that if we do that, so we're now changing the interconnect a little bit. So the demands that we're asking from the interconnect are now a little bit more complicated. Before I said we had a replicate operation and an all reduce. Now we have reduce scatter and all gather. And we're sort of alternating between reduce scatter and all gather. So this change saved us a bunch of memory, pushed a little bit more on the interconnect. The combination of reduce scatter and all gather should be the same amount of memory traffic on the interconnect as an all reduce. So it seems like it should be about the same, but it does require more flexibility from the interconnect. So another example of how all of this needs to be optimized together. And that all these things together is giving us the results I've been talking about, where we get 56% MFU, and we're also able to scale to really large models. Okay, now we're really proud of our scaling. Weak scaling is great when you have a problem that can weak scale. But as a community, we've been learning some things, and DeepMind came out with a paper called Chinchilla that showed that we've been undertraining the models. We really need to train the models on a lot more data than we thought. And that means that we need smaller models that are just trained much longer, which you can imagine from a systems point of view isn't maybe what we wanted, right? Because it means more sequential steps, right? We just like increased the number of sequential steps in the algorithm by like a factor of 5, and then we've reduced the amount of work per step by a factor of 5, right? So like computationally, this is going to be pushing on the system a lot more. We're going to need to be thinking about strong scaling. And also, if inference is our most important workload, I've been talking about the training problem because we've been trying to get AI off the ground. But now that ChatGPT is here, people are using it, inference workloads are so much more expensive. Actually, maybe we should overtrain the model. If we can make the same size model even a little bit better, then that could cut back on our costs to deploy it. Maybe that's worth doing. Invest more in training, make inference cheaper. And so this pushes on strong scaling, reduces batch sizes, and also pushes on the interconnect a lot more. And so we've been working on that. I think we have some decent results here. It takes 13 days on 2,000 A100 GPUs to train a GPT-3, but we'd like to make that better. We think there's more opportunities, and there's been some other great ideas that have come up. Flash attention was a great idea that came out last year, which basically takes a look at one of the most important blocks of the transformer and rewrites it according to the memory hierarchy of the GPU. So basically, it avoids having to materialize things in memory. It's kind of doing it on the fly, loading all of the data sort of block by block, and then computing intermediate results in on-chip memory in sort of a fused way. And that has been really helpful because it reduces memory bandwidth, which then helps us with our strong scaling. So for training a smaller model, a 20 billion parameter model, we're seeing about 20% end-to-end speed by using this. So our MFU goes from like 44% to like 52%, which is pretty important. We're also working on overlapping more compute and communication. We have the round robin pipelining with our interleave pipeline schedule. And the way that we had been doing it was we would actually do the forward prop and the back prop, and then we would synchronize and send data around. But you can imagine that it would be better if we could do the forward prop, send the result to some buffer somewhere, do the backward prop, and then have the next forward prop just read from that buffer in parallel. And that is an interesting thing to try to do. It's somewhat difficult because now we need to have multiple programs running on the GPU at the same time. And how much of the processor are we going to devote to communication versus computation? So that's kind of an interesting question. And then we also have more opportunities for overlap for some of the other places as well. So for example, in the tensor parallel work, we have this all gather stage, and what we're doing is actually breaking things up by sort of using a ring to compute each stage in parallel and communicate in parallel. So we kind of, if you imagine S distributed across 4 processors. We have each processor multiply S, its copy of part of S and part of H, and compute something. Then we, at the same time, we're moving its block of S around to the next processor, so that by the time it's done finishing the first block, we can start on the second, the third, and the fourth. And the idea is that if we can do all of this in parallel, then we can further improve our strong scaling ability. So again, these are the kinds of optimizations we're thinking about. Now, when I've been talking about compilers, could we make a compiler to do this? Yes, we could. We could totally make a compiler to do this. And it would be great if somebody did that. I think one of the problems is that the field is moving quickly, right? So like the idea that we've been under training the models, we need to do dramatically more training, we need to do more strong scaling. That's come across, basically, in the past year or so. It takes a long time to build a compiler. Meanwhile, we're moving, the field is moving. The demands on a compiler are that it needs to be pretty flexible in order to handle the speed at which things are moving along. But I believe it could be done, and I would love it if one existed. Okay, so for the end of my talk here, I just want to talk about math a little bit. Numerics are really, really important. Training these models is numerically challenging. In fact, when we started training, we trained a few years ago, we trained a 530 billion parameter GPT model, and we were really proud of it at the time. Unfortunately, the first 6 months of that project were derailed because of numerical instability. And we had some work to do on our algorithms, our actual solver algorithms. At the time, we were using IEEE floating point, 16-bit floating point. And it turns out that the dynamic range of IEEE 16-bit floating point is challenged when training large language models, but not when training small language models. So they train fine as long as they're small ones. When you go to a big one, they break. And of course, the instinct is to think, well, my code has a bug in it, right? Like maybe there's a memory overflow or something. Actually, it was a numeric problem, and it took a while to prove that and then to fix it. So we're pushing these models right to the edge of numerical stability, and we should, because they're so expensive to train. We need to think about numerics very carefully. On the GPU, we have these tensor cores, which are optimized for dense and slightly sparse matrix math. This little, I don't know if you can understand the cartoon on the right. It's actually showing what a matrix multiply looks like. It's kind of showing the n cubed compute and n squared inputs and outputs if you tilt your head the right way. And so we've had 5 generations of GPUs with these tensor cores in them designed for AI number crunching. There's different numerical formats that they support, and over the years we keep changing them. With Hopper, we have introduced 8-bit floating point, which is pushing it a little bit, right? 8-bit floating point, like what exactly is that? Well, in Hopper, we actually have 2 FP8 types. We have what we call E5M2, 5 bits of exponent, 2 bits of mantissa, 1 sign bit. And we also have E4M3. And they're slightly different. On the right, you can see what happens when we try to represent a number. So there's like an FP32 number, 0.3952. And there's a FP16 representation. There's a BF16, so the brain float, that's Google's format. It has the same exponent as an FP32, so 8-bit exponent, but then it has a smaller amount of accuracy, smaller mantissa. And so you can see that instead of 3952, we've got 3954 for BF 16. And then E4M3 FP8 is even worse. We're at 0.406, and E5M2 we're at about 0.375. So you can see there's accuracy trade-offs here. There's also range trade-offs, right? So we want a big numerical range in order to compute all the intermediate steps in the optimization process. So we've done a lot of work to figure out how to use these formats and incorporate them into our training algorithms. With Hopper, we're actually doing our training in FP8. In order to do that, we have hybrid algorithms that use FP32 for part of it, FP16 for part of it, FP8 for the most math-intensive parts. And the hardware is designed as kind of a hybrid system as well, where it accepts operands in different formats, including E5M2 or E4M3 or FP16, and then is computing everything, usually producing a higher precision output, which then can be operated on and potentially stored in memory or rounded in order to go into the next stage of the computation. So what kind of speed up do we get from that? We get up to 2x speed up with FP8 compared with FP16, although you could imagine that it's best for really big matrices. You can see here that our speed up is going to be smaller if the matrix is smaller. So there is some speed up to be gained there, and then when we train models, it's important that we get the numerics right. So here's some results of some training runs that we've done in FP8. I think the most important ones are the purple one at the bottom that's sort of showing that our 175 billion parameter GPT-3 is converging using FP8 as the math format. And with all of that, we can get a speed up of about 3x for GPT models on an H100 over an A100 running on 64 GPUs. So, okay, I've come to the end of the talk, which is good because we're out of time. What I wanted to kind of give you a sense of today is the scope of some of the work that I've been involved with, that the industry's been working on with training and deploying these language models. I really believe that given the impact these models are having on so many different parts of the work that we do as a society in so many different fields, that training and deploying these models is the biggest compute challenge of our time. And I feel like you guys, you're experts in compute challenges in different aspects, whether that's computer architecture or accelerator design or networking or compilers or libraries, frameworks, ways of thinking about programming models. All of this, they all come together, right? So all of the results that I've been showing require every aspect of the system to be working flat out, and that's what accelerated computing means to me, is that we need to optimize everything together. I think in the future, these models are going to get more diverse. They're going to be more multimodal. So there's going to be more different kinds of inputs and outputs. There may be more specialization that may involve more demands on the systems, more demands on the networking, more demands on the compute. I think it's going to be more heterogeneous, more interesting. And then I think, the deployment of these systems is also really quite interesting to think about. Let's imagine that we have an enormous data center that's just doing deployment of these systems. But it seems reasonable that the queries that are going to be coming in might have some relations to each other, just because humans tend to do things that are related. If we were able to kind of aggregate those, we might actually be able to find some efficiencies in the way that we deploy these models in kind of non-trivial ways that have to do with like load balancing across a data center. In addition, we have other things to look at: sparsity. I talked about sparse math instructions in our tensor cores, but I didn't talk about how we're using them in this talk, but there's opportunities there I think are important. Things like mixture of experts, changing the way that the model is structured, that could actually reduce the amount of memory that we have to move around during deployment. So there's like a ton of different kinds of optimizations at every level of the system, all the way from the chip to the algorithm and the application itself. And I think that represents kind of a golden age for AI systems. There's tons of it's a very tightly coupled system, right? Changes in the system have big impacts on the algorithms. Changes in the algorithms have big impacts on the systems. And so I imagine that as these language models end up changing the world economy, they're also going to change computing systems. And I think that should be exciting. It's exciting for me, and I hope it's exciting for you as well. So with that, I'm done, and I'm happy to take questions.
Thank you, speaker.